from National Technical University of Athens in Greece, and his title is Discrete and Continuous Non-Self-Adjoint Operators. Vassilis, please go ahead.
Thank you, Tunchai, and thank all the organizers and also all the participants for the nice talks. It's been a nice conference. My talk will probably concentrate on the continuous case. My abstract is a little obsolete, but because the discrete part is published anyway, so you can find it published. So let me start with the continuous case, and if there is some time, I may mention some things about discrete, or during my talk, I might mention some things about the discrete case. Okay, so here is the main object of the talk is the Hill operator, which is this operator H, where Q is a complex value potential, and it's 2 pi periodic. We can normalize the period to be 2 pi. The operator is on the whole line, and if Q is real valued, and it has to be has some kind of nice property like locally square integrable, then H is self-adjoint. For the self-adjoint case, there is a huge amount of papers, number of papers written. But also in the case where Q is complex valued, there is a lot of papers. There are works by Tkachenko and other people like Gestesi and many others, even in the complex, in the non-self-adjoint case. The non-self-adjoint case is more challenging mathematically. That's one reason to study, but also there is this other, I don't know if you have heard the PT symmetric quantum theory. The parity is called, it stands for parity time symmetric quantum theory, which allows operators, Hamiltonians, which are not Hermitian, which means self-adjoint, especially in the case where the spectrum is real. So that's an additional motivation for studying non-self-adjoint problems. So let me review for some elementary facts, which are called Floquet theory. This is the key to the spectrum in the periodic case. So we start with the equation, the spectral problem, Hy equals lambda y, and we can use either the lambda as the spectral parameter or k, where lambda equals k squared. The spectral parameter is complex. And it's a very usual thing to consider these two solutions. I will call them U and V, the cosine-like and the sine-like, you can call them, where U is 1 at 0 and the derivative is 0, and V is 0 at 0 and its derivative is 1. The Vronschian, of course, the Vronschian of U and V is 1. And then in this case, we have two linear independent solutions. Now there is a smooth dependence on the parameter lambda and k, of course. And these solutions as functions of lambda, it's well known that there are, this is not true only in the periodic case, this is always true, that there are entire in lambda of order at most one half. Now in the unperturbed case where Q is identical to 0, let's call this the unperturbed, or you can call it the free case, I don't know. The solutions U and V become the cosine squared of everybody knows, and that's a trivial observation, but I wrote it here for completeness. And the V solution becomes sine square root of lambda x over square root of lambda. When I put a tilde, I will refer to the unperturbed case. So if a quantity has a tilde, that means that it refers to the unperturbed case. Now, the Floquet theory is based on a very, very simple observation. You consider this shift operator, they call it also monodromy. So you take a function and you the shifted function is f of x plus 2 pi. You shift by a period. Now, since Q is periodic, if you take a solution of this the spectral problem, we always have in mind this equation, right? The equation 1. So if you have a solution and you shift it, then you get again a solution. You can say this in more fancy terms, that the shift operator commutes with H, to the operator H. And based on this simple observation, we can develop all this Fouquet, as they call it, Fouquet spectral theory. So we consider this operator, the shift operator, on the space of solutions for a fixed lambda. And then we have the solutions, of course, form a two-dimensional space, and S acts on this two-dimensional space. So it has a matrix. We can use the solutions U and V to write for this basis of solutions to write the matrix of S. And this is what is the matrix of S. Okay, so this is called the Fouquet or monodromy matrix. Is the solutions evaluated at 2 pi and the derivatives evaluated at 2 pi. Of course, the determinant of this matrix is the Wronskian, so the determinant is always 1. Of course, S depends on lambda, the determinant is always 1, there's no dependent on lambda. Then we look at the eigenvalues of the Fouquet matrix. So we write the characteristic polynomial, and this is how it looks like because the determinant is 1, so we have the characteristic polynomial it's a quadratic polynomial where the delta is a trace of the matrix, and this delta, the function delta, which is a trace of the matrix, is of course u plus v prime evaluated at 2 pi. And this is an important quantity for the spectrum. It's called the Hill discriminant, or it has also other names, like Lyapunov function, probably it also has other names. And you can prove that this entire of order 1/2. And we can use, as I said, the other parameter k. If I use lambda, the discriminant will be denoted by delta. And if I use k, which is the Latin letter, we can use d for the discriminant. It's the same function, of course, expressed either in k or lambda. Of course, since delta of lambda is entire, and we have delta of k squared is an even function. If I look it as a function of k, is an even function and is entire, of course, and has order 1 because delta has order 1/2. Now, there is a very interesting result by Tkachenko, which characterizes all the functions d that they can be discriminants of a Hill operator with a complex potential, which is locally square integrable. A necessary sufficient condition to be a discriminant is to have this form, see? And this bracket Q is the average of Q on one period. And all these functions are specific functions. Here you have this function H, which is free. I mean, you can use it, choose it almost any way you like, but it has to be, of course, even, because the whole thing is even. And also it must satisfy these two conditions. On the real axis, the integral is finite, but the L2 norm is finite. And also on the half integers, the sum of the absolute value is also finite. So it's little L1 for the half integers. That's a nice characterization, complete characterization of the discriminant. So coming back to the Fouquet matrix, we look at the Fouquet, the eigenvalues of the Fouquet matrix. And there are, of course, two eigenvalues. It's a 2x2 matrix. And because the determinant is 1, they have to have product 1. So 1 is the inverse of the other. The sum of the eigenvalues is the trace, so is delta. And of course, we can solve the quadratic polynomial and see what the eigenvalues are, which depend only on delta. Because if you remember, I mean, clearly, I mean, the characteristic polynomial is just this very, very simple quadratic polynomial. So the roots are just this elementary school or junior high result. Now, given the eigenvalues, we can look at the eigenvectors of the corresponding eigenvectors, which correspond to the so-called Fouquet solutions, because every solution corresponding to, if you have a solution associated to this eigenvalue, then the shift must be a multiple of the solution. And the multiplier is the Fouquet multiplier. So this, the corresponding eigenvectors are the solutions that we call Fouquet solutions, and they satisfy this. There are eigen functions of the shift operator, and the corresponding eigenvalue is the Fouquet multiplier. Now, if we have two different Fouquet multipliers, then we have different Fouquet solutions that are linearly independent. The only way not to have linearly independent Fouquet solutions is if the two Fouquet multipliers are equal. So the matrix may have a Jordan anomaly. So to be equal, since one is inverse of the other, they have to be either both 1 or both minus 1. Equivalently, the delta has to be either 2 or minus 2. In this case, we may not have two linearly independent Fouquet solutions because we have only one, essentially one eigenvalue of the Fouquet matrix. It may happen, though, that you still have two linearly independent Fouquet solutions, and in this case, we use this word, the term coexistence. So coexistence means that we are in the case where the multipliers are equal, and still we have two independent Fouquet solutions. Also, instead of having two multipliers, we can look at them as branches of one function, rho, defined on the Riemann surface of the function square root of delta square minus 4, which is generally not compact because this may have infinite many zeros, the quantity. Now, if we look them as one, if we look at a single Fouquet multiplier, then it satisfies this because rho and the inverse of rho must be the trace of the matrix, which is delta, and rho has this property. And we can call this the Fouquet multiplier with the two branches, rho 1 and rho 2. Now, there is some interesting things about rho, that they cannot have, rho cannot have neither zeros nor poles because delta is entire. So you cannot have, rho cannot be 0 because of this 1 over rho, cannot have a pole, and cannot even have essential singularities. So the only singularities of rho are branch points and square root branch points because it's just, you have only one square root in the formula for rho. So the only possible branch point, the only possible singularities of rho are branch points. And this can happen only if rho is plus minus 1 or delta is plus minus 2. Now, it should have at least one branch point, because if it has no branch points, then it has to be entire. And if it is entire, it has order less than 1/2, it has to be without zeros, it has to be constant by Hadamard's theorem. And this is impossible. Rho cannot be constant because delta is not constant. We have seen the form of delta is an entire function of order 1/2. So rho has at least one branch point. You can play a little more with that. You can find the logarithmic derivative of rho, but let's skip that. Now, if rho is 1 or delta is 2, that's equivalent, then we have a period. Then the corresponding lambda, which makes rho 1, is a periodic eigenvalue because the Fouquet solution is periodic, is 2 pi periodic. If rho is minus 1 at some lambda, then this lambda is called anti-periodic eigenvalue because the corresponding solution, the corresponding eigenvector, the corresponding Fouquet solution is not quite periodic, is what we can call it anti-periodic or 4 pi periodic. There are some, but I call it anti-periodic. So if you shift it by 2 pi, you don't get the same function, you get the function minus a sign. Now, S may not be diagonalizable if the two Fouquet solution, the two Fouquet multipliers are equal, which means if rho is plus or minus 1. In this case, S of lambda, the Fouquet matrix, would be similar to some Jordan canonical matrix. So in the case where rho is plus minus 1, S may not be diagonalizable. Now, if lambda star is a 0 of delta square minus 4 of even multiplicity, then rho does not have a branch point at lambda star, right? Because the square root will cancel with the even multiplicity of lambda star. But still, it can happen that the Fouquet matrix may not be diagonalizable. I call this a pathology of the second kind at lambda star. If you have no branch point at rho at lambda star, but still the Fouquet matrix will not be diagonalizable. This, in the real case, in the self-adjoint case, this cannot happen. But in the complex case, it can happen. Now, if we have coexistence, as if you remember, then we have two linear independent Fouquet solutions, and then the Fouquet matrix is diagonalizable, and it would be equal to, it's not just similar, here is equal to one of these two cases. And if here is the periodic eigenvalue case, here is the antiperiodic for coexistence. If lambda star is a periodic eigenvalue for which we have coexistence, then delta lambda minus 2 has a 0 of multiplicity at least 2. And if is an antiperiodic eigenvalue for which we have coexistence, then delta lambda plus 2 has lambda star is 0 of delta plus 2 of multiplicity at least 2. So in some sense, we can say that the algebraic multiplicity is always bigger than geometric multiplicity. Okay, this is always true somehow. Now, why is this true? Why coexistence implies that the multiplicity is bigger than 2? Because we can compute the derivative of delta, and this is the formula for the derivative. And if we have coexistence, then both U and V are periodic or antiperiodic, depending if we are in the periodic and the periodic case. So if U and V are both periodic, for example, then U of 2 pi is 1, because it's the same as U of 0. And V prime of 2 pi is 1. So these two terms cancel. And then V of 2 pi is 0, because V is periodic and V of 2 pi is same as V of 0, which is 0. And U prime of 2 pi is 0, so the derivative of delta is 0. So that means that if we have coexistence, then at this lambda, the derivative of delta is 0. And we have a double 0, the corresponding equations for delta. Now, how do we characterize the spectrum of the operator? Well, the spectrum has to do with the case with the lambdas for which the solutions do not grow exponentially or faster than a polynomial, say. Now, if rho has no absolute value 1, then think about the Fouquet solution. The corresponding Fouquet solution will grow exponentially in one direction, either as x goes to infinity or minus infinity. So the spectrum is characterized by the lambdas for which the absolute value of rho is 1, the Fouquet multiplier. In this case, we have bounded, or at least as we linearly growing solutions, which still are generalized eigenvalues. So this is the characterization of the spectrum. We can write it in many different ways. We can say that rho is e to the I theta, where theta is between 0 and pi, or we can use delta for the characterization. Delta has to be, because delta is, as you remember, the rho plus 1 over rho, so delta has to be real and in the interval minus 2 and 2. So the lambdas for which delta is in the interval minus 2, 2 is exactly the spectrum. It consists, is what the lambdas make up the spectrum. we can also write this in this way. Is the same thing. So that we get a very nice characterization, simple characterization by using delta, for example. That's why delta plays this central role in the spectral theory, and it's called the discriminant for some reason, for this reason maybe. Now, sigma is unbounded because delta is entire and has infinitely many, and it takes these values infinitely many times. It's entire of order 1/2. This is since it is entirely less than 1, Hadamard factorization tells us that has infinitely many zeros, for example. So we have, and the zeros are not accumulating because it's entire. So, for example, this is one reason why the spectrum is unbounded. Now, there are better characterizations due to Tkachenko, Gestesi, and probably others. Sigma is a countable system, union of analytic arcs. And the analyticity of such an arc may fail only at the point where the derivative of delta is 0, for a point lambda in the spectrum, of course. Delta of lambda has to be in between -2 and 2, and if the derivative is 0, then we may have crossing of arcs. The resolvent set is path connected. The complement of the spectrum, it's path connected. Which means that you cannot have loops in the spectrum, closed curves, not even the spectrum cannot be a piecewise analytic curve without endpoints, because that will separate the complex plane into, it will not be, the complement will not be connected. Also, asymptotically, the spectral arcs, these arcs of the spectrum, approach this half line, which is parallel to the real axis, shifted by the average of Q, and goes to plus infinity. It's unbounded on the right, let's say. Of course, periodic eigenvalues and antiperiodic eigenvalues are in the spectrum, because for such a eigenvalue, delta is ±2, and this is kind of the edge of the spectrum. I'm interested in this talk in the case where sigma is the half line. But let's make it a little more general. Suppose that sigma is just an arc, one single arc. Okay, so as we said, since the complement of sigma in the complex plane is path connected, sigma must have an endpoint, right? Say, let's call it lambda 0. We can replace Q by Q minus lambda 0 and make this endpoint of sigma to be 0. Now let's take a lambda in the spectrum, let's call it lambda star, a fixed lambda in the spectrum, which is not the endpoint. So you think of the spectrum as an analytic arc. We exclude the endpoint, which is lambda 0, which is 0, and we take a lambda star in the spectrum. I call it an interior point of the spectrum. Then we take the Taylor expansion of delta about lambda star, and it should look like that. Sorry, not of delta. Yeah, because because I think of delta of lambda star to satisfy this equation, to be anti-periodic or periodic eigenvalue, right? So delta of lambda star square minus 4 is 0. So that means it's either a periodic or anti-periodic eigenvalue. And I consider it, since it is in the spectrum, but I take it to be interior, which means exclude the endpoint. Then, of course, the delta can be expanded near lambda star like that, a Taylor expansion. Now, what could be the first term after the constant term of the Taylor expansion. Because this lambda star is interior, the C is non-zero. It's the first term of the Taylor expansion after the constant. So C is not zero. What could be the D? D has to be 2. That's the only case to get, because the spectrum is the inverse image of -2, 2. And if you think about, there's no way to have the inverse image of -2, 2 to be an arc without crossings or endpoints, if D is not 2. That means that the square root of this quantity has a double zero at lambda star, so lambda star cannot be a branch point of rho. So if the spectrum is a single analytic arc, the only branch point of rho will be the endpoint of the spectrum. And in this case, we have taken it to be 0. So rho has a single branch point. That means that rho must have this form, f of squared, because of this branch point, because the point is 0. The branch point is 0. Rho has to be a function of square root of lambda, which is entire, because there's no other branch point. And we can use the other parameter k. So rho is f of k, where f of k is entire, and has order 1, because rho has order 1/2 in lambda, so in k has order 1. And no zeros. Now, 0 is a branch point of rho. And remember, at branch points, rho has to be either plus or minus 1, because it would be either periodic or anti-periodic eigenvalue. So rho, since it is entire of order 1 and no zeros, it has to be an exponential function. And that 0 has to be plus minus 1. So it has to have this form. For some complex number alpha, which is not 0, of course, because then we have there's no way to have 0. Alpha cannot be 0. Now, the discriminant, which is rho plus inverse of rho, has to have this form then. But we have this general characterization of Tkachenko, and from the general characterization, it follows that alpha has to be 2 pi. And the average of q minus lambda 0 will be 0, which means that the average of q must be lambda. If we don't make this initial normalization of the endpoint of the spectrum, the average of initial q has to be lambda 0. Now, delta has to have this form because of the characterization, and that means that rho must be exactly like that. This is exact form of rho. In the case that we have, in the case where the spectrum is a single analytic arc. But if rho is this, then the spectrum must be, because if you remember the characterization of the spectrum, if you use rho or delta, then the spectrum is the half line, 0 infinity, the half real axis. Now, if we don't normalize q to have average 0, then the spectrum will be the half line shifted by the average of q. Okay. Now, rho 0 is 1 from here, which means that 0 is a periodic eigenvalue. Also, if you take the derivative of delta, delta is a specific function. The derivative is this one, and the derivative of delta at 0 is not 0. So delta has not have a, so there is no, if the derivative of delta at 0 is not 0, then we cannot have coexistence. Remember, if we had coexistence, at that value of lambda, the derivative of delta is 0. And in this sense, I say that S of lambda does not have a pathology of the first kind at 0. Pathology of the first kind means that that we have a branch point of rho, and at the same time we have coexistence. These things do not happen in the self-adjoint case, but they happen in the they can happen in the complex case. But at 0, at the initial point of the spectrum, we cannot have this kind of pathology, right? We cannot have we cannot have a case where we have coexistence and branch point. Branch point we definitely have, but at the same time, we do not have coexistence. I will remind you the self-adjoint case for a few minutes. None of these pathologies can happen. Lambda star is a double zero of delta minus 2 if and only if we have coexistence. And lambda star is a double zero of delta plus 2 if and only for periodic solutions. And for antiperiodic, delta lambda is a double zero of delta plus 2 if and only if we have coexistence of antiperiodic. Delta square minus 4 cannot have zeros with multiplicity bigger than 2. Notice that in the general characterization of Tkachenko, you can have multiplicities of any order. So for the self-adjoint case, we have, in some sense, equality of algebraic and geometric multiplicities. A point lambda star is a branch point of the Floquet multiplier if and only if S of lambda star has a Jordan anomaly, so that we don't have pathologies of this type. Now, the spectrum is in the real case, the spectrum is a union of closed intervals, which are called the bands, separated by open intervals, the gaps. So we have this situation. Sigma of H is a union of these intervals in order. The first eigenvalue lambda 0 is periodic. Then we have two antiperiodic, which may be equal. Then we have two periodic, again made in this are the endpoints of the gap and also the antiperiodic endpoints of the gap. And then we keep going like that. If for some n we have lambda 2n minus 1 equals lambda 2n, then the corresponding gap is closed. We call it is empty. We call it closed sometimes. The cap of the spectrum closes, but it's an empty gap. And we have coexistence for these lambdas, which is a unique lambda, of course, because they're equal. If they are not equal, if the gap exists, is not open, it's an open gap, is not empty, then we don't have coexistence at the endpoints of the gap. We have either periodic or antiperiodic eigenvalues, but no coexistence. Now, if we look at the Dirichlet spectrum, the Dirichlet spectrum is the set of zeros of V at 2 pi. The V is a function which is 0 at 0, and V at 2 pi, if it happens for some lambda to be 0, then this lambda is the Dirichlet spectrum. In general, I'm talking here generally, the V of lambda may have multiple zeros. So the set of distinct zeros coincide with this spectrum. In the self-adjoint case, the zeros of V 2 pi are simple and real, of course, because we are self-adjoint the problem. That's what the problem is. So this is the problem self-adjoint. And again, we have this equality of, if you want, you can call it equality of algebraic and geometric multiplicities. Now, even without without explaining why the zeros are simple for the moment, let's think of the following. Suppose we are in the self-adjoint case, and V of 2 pi for some value of lambda equals mu, it's 0. So mu is a Dirichlet spectrum, and the Floquet matrix at mu, remember the matrix, this entry is V at 2 pi, so here we have a 0. I'm talking about the self-adjoint case now. This, what I said is in general, but I'm referring to, I like to restrict to the self-adjoint case. So here is this Floquet matrix at a mu, which is a 0 of V at 2 pi. Now, what are the eigenvalues of this matrix? Well, the matrix is triangular, so the eigenvalues are U of 2 pi and V prime of 2 pi. So these are the Floquet multipliers. Because the eigenvalues of S is the Floquet, but these are real numbers. we are in the self-adjoint case, and mu is real, and everything is real. So also the determinant of the Flekian matrix is 1. So the product of u and v prime is 1, which means that the sum of the trace has to be at least 2. Like if the product of two real numbers is 1, I should say here the absolute value, sorry, the absolute value of the sum. Sorry. So the absolute value of delta at mu is at least 2, which means delta it's either less than -2 or less or equal to or bigger or equal to 2. So it has to, mu has to be at the edge of the spectrum, right? It cannot be interior of a band. And what happens really is that in the picture that I gave you before, we can put also the mu's. And we have first a periodic eigenvalue, then we have two anti-periodic, and in between a mu, a Dirichlet eigenvalue, which they may all be equal, or 2 or 3 of them can be equal. All equal if the gap is closed. Then we have two periodic eigenvalues, lambda 3 and lambda 4. In between, we have a second. This is the second gap, and we have another mu and so on. Now, this is basically the whole theory of the self-adjoint case. And there is a very, very short proof about that, which I haven't seen it in the literature. Maybe you have seen it. It's extremely short proof. You check all this, what I said, the multiplicities of the u, of the v's, and all that. You check it for the zero potential, the unperturbed case. And this picture is true, holds. And then you perturb, you do this continuous deformation of the potential from the 0. You take this parameter t from 0 to 1, and you go from the zero potential to the potential that you are interested in, which is real potential. And everything moves continuously. All the zeros, and they stay on the real axis because of the self-adjointness. All these are eigenvalues of self-adjoint problems. So this picture remains. And that's the whole thing. And the zeros cannot become double, or if they're simple, or they become only if at the edge of the gaps. They cannot go through bands. So the mu stays simple zeros since there are simple zeros for the unperturbed case. So all the results can be proved very easily by just looking at this deformation. Sometimes I look at some books that they have long proofs of all these things. I don't know. The whole proof is this. That's why I mentioned this. Now let's go to a theorem of Borg. We all know this famous paper of Borg. I don't know how to read it. I have read it. I have managed to read it in German. Now I think you can use Google translation and translate it to English. It's a very nice paper. Of course, everybody knows that. And it has tons of results. One result in Borg is that if you have a real value potential Q, periodic, and locally in the square in the graph, and the spectrum is the half axis, then Q must be 0, almost everywhere. In fact, Borg proved a more general result, proved that if all the antiperiodic bands, gaps are closed, if all the antiperiodic solutions are, we have coexistence, let's say, for all antiperiodic solutions, or if the gaps, equivalent, if the gaps corresponding to antiperiodic eigenvalues are closed, then the period of Q is not 2 pi, but it's pi if you start with the 2 pi. Probably Borg starts with pi, I think, I don't know. But the period has to be half of what you have started with. And then if you repeat this argument, you get the period to be 1/4, 1/8, and then it turns out that this statement implies that if all gaps are closed, then the potential must be 0 almost everywhere if you assume only L2 log. And my question, which started my whole inquiry on this area, is if there are analogs of or extensions to Borg's theorem in the self-adjoint case, in the non-self-adjoint, in the complex case. In other directions that I'm not going to discuss, is that if the potential is not periodic but quasi-periodic, let's say sine x plus sine square root of 2x, or limit periodic, limit of periodic functions, which is not periodic because the periods get maybe half and half, half a quarter, so get larger and larger. So in these cases, I think Borg's theorem is not true. Maybe somebody in the audience knows more about that. But that goes beyond my talk. In any way, my interest is what happens to Borg's theorem if Q is complex. Well, there is this Gasimov's discovery, which, because even physically, I don't know, if you allow complex potentials, and suppose you have such a material or whatever, we are talking about, of course, something very ideal and very one-dimensional. Suppose you have some kind of strange material or whatever, and you have that the spectrum is the whole axis. So you have the electrons, whatever, take every energy. Borg says that you must have empty space. But if you allow complex, whatever, material or some complex matter, then you can still have something that is not detectable because all the electrons go in freely, but then something may be there. So, Gasimov discovered the following, that if you take Q to have a Fourier expansion like that, which has only positive frequencies, see, you don't have negative power, negative imaginary powers, negative frequencies here. And you can make a normalization to make this thing converge. And you look at the corresponding equation, then he constructed this Fourier solution for this problem, where the coefficients C do not depend on K, so K appears only in this denominator, and you have this C to the IKX, and this part is periodic, of course. So this is a Fourier solution of this problem. But this Fourier solution, well, these are some estimates that we don't have to worry about for the moment. This Fourier solution, the corresponding Fourier multiplier is e to the 2 pi ik, which is this, which means that the spectrum is this. So all these potentials, which is a huge family, have spectrum, which is the half line, the half real line. Now, this phi that he constructed is meromorphic in K, and the poles are simple, and the only poles are the negative half integers. So if you take phi of x minus k, you get another Fourier solution, unless you hit a pole, of course. And also, these two solutions are linearly independent, except if k is a pole where this is not defined, if minus k is a pole, maybe, or if k is 0, because when k is 0, you get the same solution. So from this, you can get the other Fourier solutions, except for some exceptions. Now, you can relax even this condition, but that's not so important. You can make it you can replace this solution, this condition, the little L1 by little L2, but we don't worry about that. And there are multidimensional analogs of Gasimov result. I think the book of Kuchman on periodic differential, partial differential operators, he discusses multidimensional analogs of Gasimov. Now the discriminant is this, because we know the Fourier exponent, there we know, hence we know the discriminant. And if we take delta square minus 4, you get a perfect square, except that when lambda is 0, it's not a double 0. Otherwise, all the other zeros here are double, because you have a square. But only at 0, because of the square root. This is the entire function, because it's even, but at 0, the 0 is not a double 0. Now, the zeros of this, of course, are half integers, squares, because as a function of lambda, we have to square them and then get half an integer. 0 is a simple 0 of this, which agrees with the fact that we cannot have at the end of the spectrum, which is at the edge of the spectrum, which is 0, we cannot have double 0. All other zeros of delta square minus 4 are double. And the only branch point of the multiplier is at lambda equals 0. However, the Fouquet matrix at the other zeros of delta square minus 4 may not be diagonalizable, although these zeros are at least double, are exactly double, sorry. And this is what I call a pathology of the second kind. The Fouquet multiplier has no branch point, but at the same lambda, we don't have coexistence because the Fouquet matrix is not diagonalizable. Now, there are many other ways to look at Gasimov's result, but here is one I like. What we can do is we can change a variable. You see, Q has this form, which means that if X is not real and it has positive imaginary part, then the Q still makes sense, converges. So we can make a substitution z equals c to the ix and end up with this equation where P is Q evaluated instead of e to the I and x, we have z. So is an analytic function in the unit circle. And even in the boundary of the circle, it converges. Now, what is this equation? We teach this in our undergraduate OD classes. This is that's a regular singular point. Z equals 0 is a regular singular point. So we look at the indicial equation, and we get that the exponent is r equals plus minus k. So the solution of this, the Frobenius solutions, look like that. If I change again z to be e to the ix, then I get that this is the Fouquet exponent. And this is how you can look at Gasimov's result. So the spectrum is 0 infinity. Here is an example of specific potential, but they're running out of time. So it's essentially this rings a bell, of course, the hyperbolic secant square. And if A is less than 1 in absolute value, then we get a Gasimov potential. If A is bigger than 1, we get something similar. And this is the Fouquet solution in this case. Here we have only one pole. For this specific potential, the Fouquet solution has only one pole as a function of k at minus m over 2. And if I change k to minus k, I get the other Fouquet solution, except if k is 0 or m over 2. If k is 0, then the other solution is not periodic. It has this linear term. The same is true if k is plus minus m over 2. Then we have the second solution, which is not periodic or antiperiodic. It has a linear term. But for all other values of k, including the integer values, the half integer values, except for m over 2, we have coexistence. We have two Fouquet solutions. But if k is equal to m over 2, then, as we see here, we complete explicitly, we don't have coexistence. Still, the m square over 4 is a double zero of delta square minus 4. So that means that the Fourier multiplier has no branch point at this lambda. And so we have a pathology of the second kind. Now here is a conjecture. Suppose that I don't know if this, I put also entire to make it a little more restrictive, and two periodic. If the spectrum is the half line, the real half real axis, then my conjecture is that Q must be a Gassimo potential or the conjugate of the Gassimo potential, which again has the same spectrum, because if we take Q and take the conjugate of Q, we get the adjoint operator and the real spectrum stays the same. And I use this terminology. I call the potential Gassimo potential, not necessarily entire, periodic function whose Fourier expansion contains only positive or only negative frequencies. Here's a small indication why this may be true. I've tried to find counterexamples and I couldn't. I came close to counterexamples, but I didn't find. In the suppose that the Fourier expansion of Q contains both positive and negative frequencies. Suppose that Q is entire. Now we make this transformation that I did before, z equals e to the ix. And then the resulting equation for z has a singular point at 0 or infinity, but you can always change it to 0. In the case of Gassimo potentials, you only get a regular singular point, and you have this Frobenius expansion. If the potential is not Gassimo and you use this transformation, then you get a singular point. That may be an indication in favor of this conjecture. Let me skip a few stuff and give you, well, we have some nice asymptotic formulas. Let me mention this trace formula that for the complex case. I don't know if you have seen, I haven't seen for the complex case trace formula, but I'm sure that they probably exist. If mu1 mu at the zeros of v of 2 pi at 2 pi, counting multiplicity, so this mu's may be repeated. And we label them so that we keep the absolute values to increase. And we assume that Q belongs to C, is a smooth potential, it has two derivatives, continuous, and the average of Q is 0. Then we have this trace formula. The sum of the mu's minus, these are the corresponding mu's of the unperturbed case. And if you take the difference of the two mu's, then the sum gives you minus Q0 at 0, over 2, sorry. This reminds the formula which is well known from Gelfand and before maybe, which for the Dirichlet spectrum, and in the case that we talk only about the interval 0 to pi and Q may not be periodic, then you have to write the formula as Q of 0 plus Q of 2 pi over 4 with a minus sign in front. Since Q of 0 equals of Q of 2 pi for the periodic case, we get twice Q of 0 and you simplify the 4, you get that. Now, this formula is well known for the real case. But in the real case, mu is the Dirichlet spectrum. Here, mu is not quite the Dirichlet spectrum. It's the zeros of V could be repeated. So maybe some of them are repeated. Now, I don't have much time maybe to show you the complete proof, but basically you estimate this integral. You estimate this integral, this quantity with the lambda in front are the sum of the zeros of V. And then this quantity with times lambda is the sum of the zeros of this is the unperturbed solution. V tilde is the specific solution, the sine square root of lambda, etc. So this integral, if you evaluate it, a contour integral on this circle, which has radius n over 2 plus 1, 4 square, this integral gives you this is the sum of the zeros of this minus the sum of the zeros of this. So is this quantity. And then if we estimate this as n goes to infinity, you end up with this trace formula. And I can finish with, I have uploaded the whole talk, so you can look at the rest. But there is another analog of Borg's theorem, which holds. Suppose that Q is C2, and the spectrum is the half line, so that the discriminant must have this form. Remember, if the spectrum is the half line, then the discriminant must be that. And suppose also that we have coexistence for every periodic and anti-periodic eigenvalue except for the 0 one. Then Q is identically 0. Now, in the self-adjoint case, the second assumption is included in the first. If the spectrum has no gaps, then we have coexistence except at 0. Here we have to assume it. Now, if we assume both coexistence and the spectrum to be half-line, then Q is 0. And maybe I will stop here. I think, how am I doing on time?
You still have 5 minutes, Vassilis.
Well, yes. Well, the proof is very simple. I have to discuss some stuff about the shifted operator, which I didn't have time to do. So I will better stop here, and maybe there are some questions that I can clarify. So I did mention, maybe I can mention one thing about there is this characterization that I told you about to say one word about the discrete case. There is this characterization of Tkachenko for the discriminant in the continuous case. I have found a characterization of the discriminant in the discrete case. And if in the discrete case, the discrete strategy, if the period is capital N, which has to be an integer in the discrete case, then the discriminant can be any polynomial of degree N. We're talking about complex potentials. Then the discrete case, the discriminant can be any polynomial of degree N, whose leading term is -1 to the N times lambda N. And the rest of the polynomial can be anything. So there is this analog of this theorem in the discrete case. This I have published in a paper in the Journal of Spectral Theory. So I'll stop here.
Thank you, Vassilis.
Thank you.
Are there any questions for Vassilis? Well, since Vassilis has his talk, I guess in the PDF format, and also there's the recording. So if there are no talks, then we thank him again, and our next talk will start in 17 minutes. Thank you, Vassilis.
Thank you.